Now we're going to talk about collisions in two dimensions. Those are called glancing collisions. And we will solve some examples on linear momentum and collisions. Okay, so if we have an isolated system of two particles, isolated in terms of force, the net external force acting on the system is zero. This implies linear momentum conservation. M1v1 initial plus M2v2 initial equals M1v1 final plus M2v2 final. That is, the initial momentum of the system is equal to the final linear momentum of the system. Now this is a vector equation, so in two dimensions this implies m1v1 initial x component plus m2v2 initial x component must be equal to m1v1 final x component plus m2v2 final x component. And then we have m1v1 initial y component plus m2v2 initial y component equals m1v1 final y component plus m2v2 final y component. So we obtain a set of two equations, one for x components and one for y components. Now let's consider an example. A particle of mass m1 colliding with a particle of mass m2 initially at rest. So m2 is at rest, m1 is moving towards m2 with an initial velocity v1 initial. After the collision, m1 moves at an angle theta with respect to the horizontal, and m2 moves at an angle phi with respect to the horizontal. So in this situation, since we have net external forces equal to zero, we have linear momentum conservation, and we can write this for x components. Now, since m1 is moving on the x-axis, we have m1 v1 initial as the initial momentum. m2 was at rest, so there's no contribution from m2. This must be equal to m1 v1 final cosine theta, x component, plus m2 v2 final cosine phi, x component. And so for the y equation, we can write, since we don't have any y component initially, 0 equals m1 v1 final sine theta minus m2 v2 final sine phi, because I'm envisioning m2 making an angle phi with respect to the horizontal axis in the negative direction. Okay, so we can write this set of two equations. If the collision is elastic, we can also write kinetic energy conservation. This would imply 1 over 2 m1 v1 e initial squared, v1 initial squared. This is the kinetic energy of m1 initially. m2 doesn't have kinetic energy. Final kinetic energy 1/2 m1 v1 final square plus 1/2 m2 v2 final square. Okay. So let's look at an example. A small block of mass 0.5 kilograms is released from rest at the top of a frictionless curve-shaped wedge of mass 3 kilograms. M2 is 3 kilograms and 1 is 0.5 kilograms. There is no friction and 1 is initially at rest, which sits on a frictionless horizontal surface. There is no friction with the horizontal surface as shown in figure. When the block leaves the wedge, its velocity is measured to be 4 meters per second to the right. So that's the final velocity of the block. What is the velocity of the wedge after the block reaches the horizontal surface? So at this instant, when m1 has this final velocity, what is the final velocity of m2? And what is the height of the wedge? Okay, so let's start in part A by noting that since we have no friction, there is no non-conservative force in action, the change in the mechanical energy of the system must be zero. There is no energy loss mechanism. So the change in the kinetic energy plus the change in the potential energy is zero. So if I write the change in the kinetic energy, 1/2 m1 v final square plus 1 half m2 v2 square, final kinetic energy. Initially it was at rest, the wedge is at rest, plus final potential energy. We have 0 final potential energy. Initial potential energy is m1gh. So this must be equal to 0. So this is final kinetic energy minus initial kinetic energy plus final potential energy minus initial potential energy of the system. Okay, so using this mechanical energy conservation, we can write, therefore, the potential energy, initial potential energy m1gh, you can see I can take this to the right hand side. It becomes m1gh on the right hand side. This is equal to the left hand side, 1 half m1v final square, 1 half m1v final square plus 1 half m2 v2 square. Now I can also see that there is no net external force acting on this system. So for the system of the wedge plus m1, we have internal forces, and plus the earth, we have internal forces. Those are the weight and the contact force in between these objects, but we don't have anything external to this system. So linear momentum must be conserved. Delta P is equal to 0. The final momentum m1 v final I hat minus m2 v2 I hat minus the initial momentum 0 is equal to 0. Delta P is equal to 0. So we find m1 v final must be equal to m2 v2. So v2 is equal to m1 divided by m2 v final, which is 0.5 kilograms divided by 3 kilograms times 4. That is 0.667 meters per second. So written as a vector, v2 velocity, final velocity of the wedge is minus 0.667 I hat meters per second. So as you can see, I have identified x and y axis here. Therefore, this is in minus I hat direction. So the energy conservation was not enough, but I'm going to utilize this information to find what h is. But in this case, the linear momentum conservation allowed me to calculate V2. So let's move on to part B. Now in part B, I can use this energy conservation equation, mechanical energy conservation, m1gh is equal to 1 half m1 v final square plus 1 half m2 v2 square. So if I try to isolate h here, this tells me gh is 1 over 2 v final square, dividing both sides by m1, and then I have 1 over 2 m2 over m1 v final v2 squared. Now v2 was m1 over m2 v final, so it is m1 over m2 squared v final squared, and m1 over m2 square is going to get rid of m2 over m1, so I'm going to be left with just a single m1 over m2, and h can be obtained as v final squared plus m1 over m2 v final squared divided by 2g, and this is equal to, if I take this into v final squared over 2g parentheses 1 plus m1 divided by m2. So h will become, v final was 4 meters per second, so it is 16 divided by 2 times 9.8, 1 plus m1 0.5, m2 3.5 over 3, which will give me the final answer 0.952 meters. Okay, so to summarize, we have a wedge. There's no friction on the wedge, there's no friction on the horizontal surface between the wedge and the surface, and one is at the top of the wedge initially. As this falls down on the wedge, its potential energy turns into the kinetic energy of m2 and m1. And during this process, since there is no external force acting on this system, on the x-axis, we have linear momentum conservation on the x-axis, so we can utilize this information. And this tells us that m1, the m1 v1 initial, which is 0, it is initially at rest, m2 v2 initial, which is also 0. So initial momentum of 0 will become final momentum m1 v final I hat minus m2 v2 I hat. And this is our mechanical energy conservation. Once again, why is mechanical energy conserved? Because there is no friction. There is no non-conservative force on this system. Using these two equations, linear momentum conservation and mechanical energy conservation, we were able to calculate h and the velocity of the wedge at the point when this block has reached the bottom surface. All right, let's move on to another example. Now again, we have a block of mass m sitting on a wedge, making an angle alpha with the horizontal. The wedge has a mass capital M, and the wedge is on wheels, so this can move. M is released from rest, just like the previous problem. What I would like to find out is the acceleration of M with respect to capital M. So, and I want to know its limiting value for capital M much greater than M. So as you can see here, as M moves down, just like the previous example, this wedge will start moving to the left with a velocity v capital M, and this is actually going to accelerate. As this accelerates, this will accelerate, but at the instant when M has a velocity v, relative velocity v with respect to capital M will have a velocity v a capital M with respect to the Earth. Okay, so let's start analyzing the situation. For this total system of capital M and lowercase m, the net external force on the x-axis, as you can see, this is the x-axis, is 0. So I have a linear momentum conservation on the x-axis. Delta px should be 0. So px final minus px initial should be 0. And this is according to an inertial observer. So who is the inertial observer? This is the inertial observer, the Earth observer watching this event. Because there is no fictitious force according to the inertial observer. And we can see that we can write this momentum conservation. And v is what I call the velocity of the block with mass m. So velocity of m with respect to capital M and the velocity according to the inertial observer is basically the velocity according to the non-inertial observer, v, v cosine alpha. So this will have a component v cosine alpha, and because it's on this reference frame which is moving with velocity vm to the left, v cosine alpha minus vm, v capital M, in I hat direction. So what is v capital M? It is velocity of capital M with respect to Earth. So that is my inertial observer. Okay, so if I write the momentum conservation according to my inertial observer here, I will have a final momentum m v cosine alpha minus v capital M I hat minus capital M v capital M I hat. The final linear momentum on the x-axis must be equal to the initial, which is 0. So I find the relationship between these velocities. V capital M is m cosine alpha divided by m plus capital M times v. So this is the relationship between the velocities, and if you take a derivative with respect to time, you find that the acceleration of the wedge according to the Earth observer is m cosine alpha divided by m plus capital M times the acceleration of m with respect to capital M, which is the question here. So I want to know what is this acceleration with respect to capital M. Now I want to look at this problem by drawing a free body diagram according to the non-inertial observer. Who is the non-inertial observer? The guy on the wedge is the non-inertial observer. Okay, so let's carefully draw a free body diagram for M from the point of view of the non-inertial observer. Okay, and I want to redefine my axis here. This is my y-axis, this is my x-axis. So this is x, this is y, and here is the angle alpha with the horizontal. And with that, if this is my particle m, there is the weight of the particle mg, that's pointing down. There is a normal force. The normal force is perpendicular to the wedge, normal force, making an angle. So this would be my direction for the normal force, 90 degrees. You can see that the normal force would make an angle alpha with the vertical axis. So this will be alpha also. This is 90 minus alpha. 90 minus alpha, you would see that this is alpha. So it makes an angle alpha with the vertical. So these are the two real forces acting on M. And now, because capital M is accelerating to the left, there will be a fictitious force the ghost force pointing in opposite direction, fictitious force, which is mass m times acceleration of capital M. And this is my particle with mass m under the influence of these three forces in the non-inertial reference frame. Okay, so let me point out that the inclined plane, my wedge here, accelerating to the left. So the fictitious force that appears in the non-inertial reference frame is pointing to the right. And the net force on the y-axis here, in this new definition of x and y axes, is equal to 0 because m is not flying away from the wedge. Then I can write, since this is going to make an angle alpha with respect to the surface of the wedge, MAM sine alpha, that is the projection onto the y-axis, normal force is on the y-axis, minus, then I will have an angle alpha here, so mg cosine alpha is equal to 0. Alpha, 90 minus alpha, alpha. Okay, so mg will make an angle alpha with the y-axis, so mg cosine alpha will be its projection. The net force on the x-axis is mass times the acceleration of m with respect to capital M. Or let me put this in parentheses, acceleration according to the non-inertial observer. So if I take the x components, then I have fictitious force x component MAM cosine alpha pointing in plus I hat direction, mg sine alpha pointing in plus I hat direction. Normal force does not have a component. This is equal to ma. So if I rewrite this equation here, this is going to be m times acceleration of capital M can be written in terms of acceleration a from this analysis here. So I can take this and plug it here for a capital M, m times m cosine alpha divided by m plus capital M a cosine alpha plus mg sine alpha equals ma. And you can see there are too many m's here, so one of these m's will disappear. I put this into a parentheses, so I will have, on the right hand side I have only a, so a parentheses 1 minus, I take this to the right hand side, it becomes a times 1 minus m divided by m plus capital M cosine square alpha, because I have two cosine alphas now, cosine square alpha is equal to this remaining term here, g sine alpha. So I have the final answer, acceleration with respect to capital M, the non-inertial observer, is g sine alpha divided by 1 minus m over m plus capital M cosine square alpha. So this is the answer to the first question. The second question was, what is the limiting value of this acceleration for capital M much greater than m? Well, in that case, the term at the bottom, m over m plus capital M, will become 0. So we will have acceleration equals g sine alpha divided by 1 minus, well, since capital M is much greater than m, this m can be ignored. It becomes 1 minus m divided by capital M cosine square alpha. When capital M approaches infinity, this is going to become 0, and therefore we will obtain the final answer. The limiting value of this acceleration is g sine alpha. Okay, so the limiting value of this acceleration is g sine alpha, and what is the limiting value of am? In that case, you can see that am will become 0 because it will be 1 over infinite, which is 0. So in that case, there will be no wheels here. This is just remaining on the ground, and this will just have an acceleration that is equal to g sine alpha. So it will be under the influence of the force mg sine alpha, which will give its acceleration g sine alpha. So this basically makes a lot of sense. Therefore, in this limit, our answer seems to work well. Okay, so just to summarize what we have done here, in this problem, again, we have no friction, m released from rest from the top of a wedge making an angle alpha with the horizontal with mass capital M on wheels, and there is no friction at the bottom surface as well. And I want to know what is the acceleration of m with respect to capital M. So if it's with respect to capital M, that is acceleration of m reported by the non-inertial observer. Why? Because capital M will start accelerating as m accelerates downward. First, I found the relationship between these two accelerations. Acceleration of capital M reported by the inertial observer and acceleration of m reported by the non-inertial observer. This was done by looking at the linear momentum conservation, because from the point of view of the initial observer, we have no external forces acting on the system, and the velocity of m on the x-axis, x component, according to the inertial observer, will be v cosine alpha minus v capital M, because it's on a reference frame which is moving with this velocity. And v capital M is the velocity of capital M with respect to Earth. And if I write the final momentum equals initial momentum, I see the relationship between velocities and take one derivative with respect to time. We see, because m and alpha are constants here and capital M is a constant, am is equal to a times m cosine alpha over m plus capital M. So knowing this relationship, I turned to the free body diagram of m in the non-inertial observer, non-inertial reference frame, and to do this easily, I have redefined my x and y axis. This is y axis, normal to the surface of the wedge. X axis is parallel to the surface of the wedge. And I identified the forces on M to be the normal force, contact force, mg, the weight, and the fictitious force, which is the mass m times acceleration of capital M. And solving for the net force on the x-axis, x-axis, remember, is now the axis that is parallel to the surface of the wedge, equals m times a. I have used the relationship I have found previously from linear momentum conservation in this result, and I obtained a as a function of alpha and the masses, and I see that in the limit capital M much greater than m, that means the wedge is too heavy, it won't move at all. In that case, the acceleration A would be just g sine alpha, and when the fictitious force is 0, you would have mg sine alpha that will be pointing in the in the I hat direction. It will be solely responsible for the acceleration of the block with mass m. Okay, let's move on to another example. Two particles with masses m and 3m are moving toward each other along the x-axis with the same initial speeds vi. Particle m is traveling to the left, particle 3m is traveling to the right. Okay, so let me draw the situation here. Particle with mass 3m traveling to the right with a speed v initial, and then I have particle with mass m traveling to the left with the same speed v initial. They undergo an elastic glancing collision, so it's two-dimensional, such that particle m is moving in the negative y direction after the collision at a right angle from the initial direction. So I see that after the collision I have the following situation. A particle with mass m is going down, making a 90-degree angle with the horizontal. This is Vm final, particle with mass m. And let me note that this is my y-axis, this is my x-axis, orthogonal axes. Find the final speeds of the two particles in terms of the initial speed vi. What is the angle theta at which particle 3m is scattered? Okay, so in this system of two particles, net external force acting on the system is equal to 0 on the x-axis, so and also on the y-axis. Delta p will be equal to 0. Delta px is 0, and therefore if I write the initial momentum 3m v initial I hat minus mv initial I hat, this must be equal to x component of m is 0, y component of 3m velocity, x component of 3m velocity, we have to determine 3m final x component. Okay, so from this equation I find that for 3m final velocity x component, it must be equal to 2 over 3 v initial. So let me note this result. On the other hand, I have delta py is equal to 0 because it's a glancing collision. There was no y component initially. Finally, I have 3m v 3m final y component, and for s for m I have a particle moving in negative y direction, so minus m Vm final y component, which is Vm final. There's only y components. So this gives me V3m final y component is Vm final divided by 3. So let me note this result here as well. Now this is an elastic collision. So I note here that this is an elastic collision. The change in kinetic energy must be equal to 0. Initial kinetic energy 1 over 2 m v initial square plus 1 over 2 3m v initial square is 1 over 2m vm final square plus 1 over 2 3m v3m final squared. And these 1 over 2's will disappear. And I want to note here that v3m final squared is actually v3m final x component squared plus v3m final y component squared. So the left hand side will become 4m v initial squared. The right hand side will be m vm final squared plus 3m v3m final x component squared, which is 2 over 3 vi squared, so 4 over 9 vi squared plus v3m final y was vm final divided by 3, so it is vm final squared divided by 9. Okay, so if I multiply both sides by 9, I obtain 36 mvi squared is equal to 9m vm final squared plus 12m v initial squared plus 3m vm final squared. So if I take the 12 to the left hand side, this becomes 24m v initial squared is equal to 9m plus 3m, 12m vm final squared. Therefore, I find that vm final is 24 divided by 12 square roots, that's square root 2 vi. Now, to find v3m final, squared was 4 over 9 vi squared plus we have vm final over 3 squared, which is 2 vi squared over 9. So that is 6 over 9 vi squared, which is 2/3 vi squared. So we can see v3m final is square root 2 over 3 vi or square root 6 divided by 3 vi. So I know the final speeds in terms of vi. And for part B, I want to know the angle this velocity vector makes with the x-axis. Tangent theta is the y component of the vector divided by the x component of the vector, v3m final x, and that is vm final over 3 divided by 2v initial over 3, which is vm final over 2v initial. Vm final was square root 2v initial divided by 2v initial. That is 1 over square root 2. So what is the angle whose tangent is 1 over square root 2? 35.3 degrees. Okay, now I want to note here an important fact. So let's take a note here. If I were to calculate Vm initial plus Vm final, the total velocity vector, initial plus final velocity vector, that would be minus Vi, so Vm initial was minus Vi I hat, and final velocity is minus square root 2 vi j hat. Is this equal to v3m initial plus v3m final, as we said for head-on collisions? Well, v3m initial was vi hat, v3m final is 2 vi over 3 I hat plus square root 2 over 3 vi j hat. As you can see, these are not equal. So for glancing elastic collisions, we cannot use the result we obtained for head-on collisions using kinetic energy conservation and linear momentum conservation. The total velocity vector initial plus final for the first particle is not equal to the total velocity vector initial plus final velocity vectors of the second particle for glancing elastic collisions. Okay, so to summarize, we have gone through an example of a glancing elastic collision. 3m initially moving with velocity vi to the right, m moving with velocity vi to the left. They collide. M starts moving in the negative y direction with vm final velocity. I want to know final speeds of the particles in terms of vi and the angle at which the particle with mass 3m is scattered. First, I wrote a linear momentum conservation. On the x-axis, initial momentum is 2 mvi, 3 mvi minus mvi. The final momentum magnitude is m times 0 because there is no x component. And for 3m, there will be an x component, v3m final x. This allows me to write v3m final x component in terms of vi, 2/3 vi. The linear momentum conservation on the y-axis, since there is no external force acting on the system, is equal to 3m v3m final y minus mvm final. And this allows me to write v3m final y in terms of vm final over 3. Then I write elastic collision, no change in kinetic energy, and by noting that v3m final square is x component square plus y component square, substituting for x and y components these two results, I obtain vm final as square root 2v initial and v3m square root 2 over 3v initial. The x and y components can be calculated separately here. If you take the ratio of x and y components, y component or x component is tangent of the angle it makes with the horizontal axis. The angle, scattering angle, is 35.3 degrees. Finally, I noted that the total velocity vector of the particle with mass m was not equal to the total velocity vector of particle with mass 3m, as it would be for a head-on elastic collision. Next example, now I have a particle with mass m velocity vi moving towards a particle, second particle with the same mass initially at rest, equal masses. What are the final velocities if I see that the final velocity x component of the first particle is 0? Once again, the total external force acting on the system is 0. I can write linear momentum conservation for x component and for y component. So x momentum mvi initially, finally I will have m first particle final velocity x component plus m second particle final velocity x component. Let's call this equation 1. The y components, there's no initial y component for the linear momentum. Final m1 v1 final y plus m2 v2 final y. Second equation. Kinetic energy conservation, delta K is equal to 0. Initial kinetic energy is 1 over 2 mvi squared. Final kinetic energy is 1 over 2 mv1 final squared plus 1 over 2 mv2 final squared. 1 over 2 m's will disappear, and I will find V initial squared is V1 final squared plus V2 final squared. This is my third equation. So you see, I don't know V1 final x, I don't know V2 final x, I don't know V1 final y, I don't know V2 final y. This gives me 4 unknowns and 4 unknowns in general and 3 equations. So if I insert this information, V1 final x should be equal to 0. So I know that the first particle will not have an x component of its final velocity. Then I will reduce this problem to 3 equations and 3 unknowns. The first equation will tell me that V2 final x is equal to V initial. The second equation will tell me that V2 final y will be equal to minus V1 final y. The third equation will tell me, kinetic energy equation, V initial squared is V1 final y squared plus V initial squared plus V2 final y squared. So the third equation was V initial squared is equal to V1 final squared. X component is 0, so V1 final squared is 0 squared plus V1 final y squared. And V2 final squared is V2 final x squared, which is V initial squared plus V2 final y squared. And for this one, if I have V1 final x is equal to 0, so for V2 final x I substitute a Vi squared, so the Vi squareds will disappear, and I will find that V1 final y is V1 final y squared is equal to minus V2 final y squared, and this basically implies that V1 final y should be 0 as well as V2 final y should be 0. So the end result would be the particle 1 stops, particle 2 moves with a velocity V2 final that is Vi I hat. So this is basically the conclusion we reach given that V1 final x is equal to 0 using this linear momentum conservation and kinetic energy conservation for this problem. Let's look at one final example. Again, I have a glancing collision between two particles, mass m, mass 2m, initially at rest. Mass m is approaching with velocity 2v0 towards 2m. Then I know that m scatters with an angle alpha with respect to the horizontal with a speed square root 3v0. 2m scatters with an angle beta with the horizontal in the negative direction with a speed v0 over 4. What are these scattering angles? Okay, so I write the total external force acting on the system is 0, linear momentum is conserved, and for the x components, I have initial linear momentum 2mv0 I hat is equal to final linear momentum m square root 3v0 cosine alpha I hat plus 2m V0 over 4 cosine beta I hat. So this gives me 2 is equal to square root 3 cosine alpha plus cosine beta over 2. Okay, so MV0's disappeared. MV0 disappears here, MV0, MV0, and I obtain this result. So this allows me to write cosine beta as 4 minus 2 square root 3 cosine alpha. So you multiply two sides by 2, 4 becomes 2 square root 3 cosine alpha plus cosine beta, so we can isolate cosine beta. The momentum conservation on the y-axis, delta py is equal to 0. This tells me the initial y component of the linear momentum is 0, must be equal to m square root 3 v0 sine alpha j hat minus 2m over 4 v0 sine beta j hat, and this gives me square root 3 sine alpha minus sine beta over 2 equals 1. Okay, so this is not equal to 1, it is equal to 0. Square root 3 sine alpha, so mv0's will disappear, mv0 will disappear, so square root 3 sine alpha minus sine beta over 2 equals 0. So I write these two results. So if you take the first equation, cosine beta equals this, so let's write this as 2 minus square root 3 cosine alpha is cosine beta over 2, and I take the square of both sides. Then I take square root 3 sine alpha equals sine beta over 2, and I take the square of this. I add these two equations to find 4 minus 4 square root 3 cosine alpha plus 3 cosine square alpha plus 3 sine square alpha equals 1 over 4 cosine square beta plus sine square beta. Cosine square plus sine square is 1. So this gives me 4 plus 3, because 3 cosine square plus 3 sine square is 3, minus 4 square root 3 cosine alpha equals 1 over 4. So I have 7 minus 1 over 4 equals 4 square root 3 cosine alpha. Okay, so cosine alpha becomes 27 over 16 square root 3. So 28 minus 1, 27 over 4 times 4 becomes 16 square root 3. So cosine inverse of this gives me alpha equals 13.0 degrees. Now if you know cosine alpha, then you know cosine beta, because cosine beta was related to alpha. Cosine beta is 4 minus 2 square root 3 cosine alpha. It is 4 minus 2 square root 3, 27 over 16 square root 3. Square root 3's will cancel. And this gives me 4 minus 27 over 8, which is 0.625, taking the cosine inverse, we find angle beta 51.3 degrees. Okay, so this was another application of a glancing collision, two-dimensional collision between particles masses m and 2m, 2m initially at rest, m initially moving with velocity 2v0 towards 2m. We know the final speeds now in terms of v0, but we don't know the scattering angles alpha and beta. So I wrote linear momentum conservation on x-axis, on y-axis, and then I manipulated the equations to obtain cosine square plus sine square terms. And with that, I was able to identify alpha, and since beta was a function of alpha, I could determine beta